grid square first. And it says this protects triangle feature and circle feature. So I want to add it. So it adds it in, and then it moves on to the next one. It says, does this one add or increase or decrease my objective function? And then it looks at it and says it doesn't have any features in it. It just adds cost to it, so I don't want it, so I skip it. But before it does that, before it actually skips it, it flips a coin. And if the coin flip is high enough, given how much it adds to your objective function, basically it can randomly include it anyway. And that's always going to be a bad decision with this one, because it doesn't add any features. But there are certain circumstances that you can think of where it would be a good decision to include it temporarily, even if it's a bad decision in the long run. And we can see that by, if we go to, let's say that it first selects this one and decides to include it, and then it selects this one and decides to include it, and now you have this reserve system set up. And now it'll go to this one and it'll say, does this add or decrease my feature penalization, or does this add or decrease my objective function? And basically it'll say, no, it doesn't help my objective function, because all three of these features are already protected. But if it adds it anyway, now it can get rid of both of these features and preserve the same amount of features in a lower overall cost, because it only has to preserve one grid cell. So it can make short-term bad decisions that then it allows it to correct for in the long term by making other decisions that are more informed in context. So it basically allows it to experiment around and make bad decisions over the short term to check to see if in the long term with different combinations those could actually be good decisions. And I know it's probably a bit confusing right now, but when you actually see how it runs through and does these iterations of sometimes making good and sometimes making bad decisions, it should be a bit clearer. So this is the actual reserve design game that we're going to be working with today. It's pretty straightforward. So these hexagons are planning units. Red ones are ones that are selected as being inside the reserve. And all of these little colored dots in the planning units are our features. They all are summed up in this table down here, which lists how many of each feature you have protected. So if you look right here, you can see that this black feature in the lower left-hand corner has a value of 2, and that's because this is protected right here and right up here as well. So this lists that. Up here you can see your boundary length modifier and your CFPF inputs that are user-defined. Temperature and cooling, you'll go over in the reading. They're about this simulated annealing algorithm, and they basically describe how willing it is to experiment with choices that seem bad in the short term. And then down here you have some of the reserve system attributes, the total cost of it, the total boundary length, the number of features you protected, and your feature penalty for not protecting the number of features, which is basically the number of unprotected features times the CFPF. And then your objective function overall, which again you want to minimize. Yeah?
I'm kind of confused on how the reserves that we're designing, how they deal with the boundary for the, I always forget the word, like the fact where how that at the boundary is limiting and the connections when this game can be so far.
So right now we have a boundary length modifier of 0, so it's not weighting connectivity at all. And this is just an example, so this is not very good reserve design. But basically the way that it takes edge effects into account is just by assuming that perimeter is bad. And so it tries to minimize the length of boundary along the entire reserve. And that's a way of incorporating these edge effects kind of indirectly. So this is the main part of the lab today. The first half of the lab is going to have you going through and kind of manually designing reserves. And then the second half will be working with this simple greedy algorithm, which is kind of less smart than the simulated annealing. And seeing how that would select an automated best preserve. And then we'll work with the simulated annealing algorithm itself to do some more optimal selection methods.